Hello everyone. This is chapter 24 and it is about capacitance and dielectric medium uh, and its interaction with the electric field. The PowerPoint file I have uploaded is revised, so make sure that you have a revised PowerPoint file for this lecture. A capacitor is a passive device which looks like this, and the unit of capacitor is microfarad or farad. Right. In a circuit board, you can take a look at this circuit board, and there are several capacitors mounted on the circuit board. These things are resistors, and those are the capacitors. And this is active switching devices in a IC, integrated circuit. And there is another circuit board which is more compact than the previous one, and this one which is labeled with C45, C44, those are capacitors, and these things are all resistors. It's a chip type resistor. These are the ICs used in the circuit board. So here and in the previous circuit board, you can see many resistors and many capacitors in the circuit board used, except for a few active ICs used in the board. And we'd like to take a look at what is the purpose and the characteristics of capacitors used in this kind of circuit board. The primitive structure of a capacitor is like this. If we have a positive charge separated in this structure and negative charge separated at this point with this structure, we have electric field from positive charge and converging to minus Q. Electric field starts from plus Q and it ends at the minus Q. And the capacitor is defined as the amount of charge stored in the system divided by the voltage. And voltage is a potential from one point to the other. And the unit of capacitor is a farad, and it's a coulomb over volt. So it's the amount of charge per voltage. That's the unit of farad. And capacitor in a device, as a device, capacitor is a structure of capacitor is like this. We have a almost infinite plate of plus charge Q and another infinite plate with minus charge Q. And if the distance between two plates, D is much smaller than the size of the dimension of this plate, and in this case, we can apply Gauss law by assuming that the distance between the two plates is much smaller than the dimension of the side length of this plate. Then we can think this is as the plate is infinite. Size of the plate is infinite. Then by applying Gauss law, with its total flux out of this plate is equal to electric field times the area is equal to Q within the volume. The volume is visualized with the three-dimensional box with a dotted line on each side. So total Q within this volume is Q in, and divided by epsilon 0 is the equal to the total flux out of this volume. Then as the flux is the electric field times the area, so if we define the area of this box is A, then total flux is E times A. So electric field is Q divided by epsilon 0 divided by A because of the Gauss law. So electric field is Q over epsilon 0 divided by A, which is the area of the plate. Voltage is electric field, integral of electric field from positive to the negative plate, and electric field is constant, so electric field times B is the integral of this. And as we have electric field Q over epsilon 0 divided with A, then we have voltage is equal to Q over epsilon 0 D over A. As the capacitance of a capacitor is defined as Q over V, we have V already obtained here, and if we have the inverse of this multiplied with Q, then Q cancels out, and we have epsilon 0 A over D is the capacitance of this device. And epsilon 0 is a constant, and so with the given epsilon 0, we can calculate, or we can obtain the capacitance in the unit of farad, and the 1 farad corresponds to 1 coulomb square over Newton times meter, which can be converted to coulomb square per joule. Joule is Newton times meter. So that's the unit of capacitor, farad. Right, we can calculate capacitance of several different structures, and the second structure we can think about is cylindrical shape, where the inner cylinder of this cylindrical capacitor is charged with plus Q, and outer cylinder is charged with minus Q. Then by using the Gauss law again, we have, if we take a volume within the inner and outer cylinder, the flux out of that volume is electrical field times the surface, with this electrical field times R, electrical field times 2 pi R times L. L is the length of this cylinder. 2 pi R is the circumference of a volume we consider. So electric field times 2 pi R times L is the total flux, and that should be equal to Q inside divided by epsilon 0. So electric field as a function of R, this one, becomes Q inside divided by epsilon 0 divided by 2 pi RL, 2 pi RL. So electric field is proportional to 1 over R, and the voltage across this two plate is electric field integral with respect to R. So that is 1 over R dr. So we have the 2 pi Q divided by 2 pi epsilon 0 L, a natural log of B over A. Where B is larger than A, as indicated in this diagram. And you use this simple relation. The derivative of natural log R is 1 over R, and natural log B minus natural log A is natural log of B over A, and so on. So capacitance is Q over V again. We have V in terms of Q, and if we substitute V with here with this, then we obtain this. So capacitance for this structure is given as 2 pi epsilon 0 L over natural log B over A. And we can calculate a capacitor which is composed of two spherical shells. The inner shell has radius A, RA, and outer shell is radius of the outer shell is RB. And outer shell is charged with minus Q, and inner shell is charged with plus Q. Then, by using the Gauss law again, we can calculate electric field within this two plate. That is, electric field is equal to Q divided Q over 4 pi epsilon 0, 1 over R squared. So in this case, electric field is proportional to 1 over R squared. Voltage is integral of electric field from one radius A to B. So it is the integral of 1 over R squared dr. As the derivative of 1 over R becomes minus 1 over R squared, we can take the integral of 1 over R squared is equal to minus 1 over R from A to B, so it's a 1 over A minus 1 over B because of the minus sign here. It's from A to B, but because of minus sign, this is 1 over A minus 1 over B. So if we use this voltage inserted in this definition of capacitance, then we have the inverse of this one multiplied with Q. So we have 4 pi epsilon 0, Q is cancelled out, and AB over B minus A. That's the inverse of this. So we have calculated the capacitance of three different structures, but that's for the exercise of Gauss law and definition of capacitance. But most of the capacitors as a device is composed of this kind of two very large plate separated with a very small distance d. So this is the basic structure of a capacitor. And if we roll this within a cylindrical shape, then we have this kind of cylinder shape capacitor. But we have a rolled two separated plates inside. It has basically a structure like this one, because it has the most efficient the largest C for a given structure. By making distance d very small, for a given volume we can make C very large. That's the purpose of making a capacitor. We need to have a large capacitor. And what is the purpose of capacitor in a circuit board? That is to store charges. So to store a large Q, we need to have a large C for a given voltage. Voltage is the potential needed to store a certain amount of Q within a capacitor. So we need a very large C to store as large charges as possible within a device. And next topic we need to consider is a series and parallel connection of capacitors. If we have a two capacitor C1 and C2 connected parallel in series like this, then the voltage across this device is added together. So voltage across this device is V1, and voltage across the capacitor C2 is V2. Then voltage is added because it is connected in series. So voltage across the device 1 is a voltage between point A and point C. So voltage across point A and point C is defined as V1 is Q divided by C1. And voltage across C to B is defined as VCB, or V2, that is Q divided by C2. And this Q and this Q are the same ones because for this is a plate, neutral plate, and this is another neutral plate. And if charges are concentrated on this plate with amount of minus Q, then charge stored in this plate should plus Q, because this plate and this connector should be neutral. And this charge is provided by a voltage or battery from external source. So if by applying voltage we have minus Q stored on this plate, accumulated on this plate, and plus Q accumulated in this plate, and because of the property of a conductor, these are conductors, we should have minus Q and plus Q concentrated on this plate and this plate. So this Q and this Q should be same. And the voltage across these two devices is just V1 plus V2. So if we add these two, Q is the same, so Q times 1 over C1 plus 1 over C2 is the voltage across these 2 points. And if we make an equivalent capacitor like this, representing these two serially connected capacitors, we can think about a capacitor one over C equivalent capacitor is equal to V divided with Q, because the definition of C is Q over voltage across it. So 1 over C equivalent C is V over Q. And Right. So V here is the voltage. That's the Q divided by C equivalent. So if we, as the voltage from A to B is same as voltage from A to B, so the if we make this V equal Q divided with C equivalent, that is same as this, so Q cancels out, and then we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So this is the equation for an equivalent capacitor representing the two capacitors C1 and C2 connected in series. So this is the equation for a serially connected capacitor. And if we have a parallelly connected capacitor C1 and C2, if we apply a voltage across these two the parallelly connected capacitors C1 and C2, charge stored over here is different from the charge stored in capacitor 2, but voltage across it is same. So by the definition of capacitance C1 and C2, it relates the voltage and the charge like this. Voltage is same in this case because the voltage across the serial connection, the parallel connection should be same. So Q1, that's the charge stored in device 1, is equal to C1 times voltage across it. The charge stored at device 2, Q2, is C2, the capacitor of the second device, times the voltage across this two plate. So total charge can be just added. The total charge, if we represent this parallel connection of two capacitors with just one capacitor, and we define C as EQ as the equivalent capacitor, and Q plus and minus Q is stored in this equivalent capacitor, then total Q is Q1 plus Q2. So total Q is Q1 plus Q2, that is C1 plus V plus C2 times V. So we have this. So by the definition of C equivalent, it is Q over V. So we have Q divided by V is equal to C1 plus C2. So C equivalent becomes C1 plus C2. So parallelly connected capacitors can be represented by one equivalent capacitor whose magnitude is C1 plus C2 plus C3 and so on. So unlike a serial or parallel connection of resistors, we have a opposite relation of serial and parallel connection of capacitors. If we have many serially or parallelly connected capacitors, we can make one of these serial connection of two capacitors with equivalent capacitor. It is 1 over 12 plus 1 over 6 is 3 over 12. That is same as 1 over 4. So the serial connection of 12 microfarad and 6 microfarad capacitor is equivalent to a single 4 microfarad capacitor. And as these three are connected in parallel, we just add this parallelly connected capacitors, 3 plus 11 plus 4, that is 18 microfarad. And there is finally another capacitor connected in series. So we have 1 over 18 plus 1 over 9. It is same as 1 over 6. Right, because that is 3 over 18. So 3 over 18 is 1 over 6, so we have 6 microfarad equivalent single capacitor for 5 serially and parallelly connected capacitors. So this is the final equivalent single capacitor representing these 5 serially and parallelly connected capacitors. Right. And next topic we'd like to cover is the energy stored in capacitor. The work done by storing a charge across a capacitor is voltage times dq, but voltage is proportional to q. So we replace voltage with q over c. So 1 over c comes out, and that's q times dq. If we take an integral from on both sides, then that's the work done, and that is 1 over c from 0 charge to capital Q charge, q times dq. So this is 1 over 2 q square. So we finally have q square, capital Q square over 2c. That's work done to store charge from 0 to the final charge q across the capacitor. So energy stored in the capacitor is just the work done by moving charges from neutral position to the final charge amount of q. Then we have energy stored in a system equals the final charge square divided by 2c. As the voltage is q divided with c, q can be replaced with c times v. So q, instead of q square, we put c square times v square, and c cancels and c times v square. Or if we just replace 1q with c times v by remaining 1q left, then q over 2c times q over c. So we have times c times v. So c cancels out, and we have 1 over 2 q times v. So these are the 3 expressions for the energy stored in a capacitor. In terms of q, we have q square over 2c is the stored energy in the capacitor. Or in terms of v, we have 1 over 2 c times the final voltage square is the energy stored in the system. Or in terms of q and v, we have right. If we have a q with a potential v, the energy stored in the system is q times v. But if v is a function of q, we have 1 over 2 multiplied to this. And so the purpose of a capacitor as a device is the energy storage device. So we can calculate the energy density, that's the definition of energy density is the total energy stored divided by the volume, because the volume of the device is, in this case, volume of device is area of this plate times the distance between this plate. That's the volume of the device. So D times A is the volume. So we divide the energy stored in the system with the volume, A times D. And for a parallel plate, C is defined by its definition Q over V, and that is epsilon 0 A over D. We have already calculated this. Oops. For a parallel plate, C is epsilon 0 times A over D. Because we calculate voltage, it is Q over epsilon 0 D over A. So by replacing voltage here with this, and we have epsilon, Q cancels out, and we have epsilon 0 A over D. So as we have C is equal to epsilon 0 A over D for a parallel plate of area A and distance, separated distance D is like this. So if we put C into this, then A cancels out, and D is becomes square of D. So that unit electric field density is 1 over 2 epsilon 0 V over D squared. A cancels out and C disappears. By replacing C with this, we have voltage over D squared. Or voltage over D is electric field for a plate. Two parallel plate, two parallel plate voltage is electric field times D, because electric field within these two plates is constant, so voltage is just electric field times D. So voltage over D is electric field, because voltage is electric field times D. So we can have an expression of energy density equals to 1 over 2 epsilon 0 electric field squared. So electric field by itself can generate energy density whose amount is 1 over 2 epsilon 0 times E squared. That's the basic property of electric field. Electric field itself contains an energy density. That's the reason why electric field itself can propagate in vacuum. We'll explain this later, but that's the basic concept of storing energy within its field. So electromagnetic wave by itself consists of electric field, and that's the reason why electromagnetic wave contains energy density within it. These are pictures of the electric field within I don't know, but I think this is a picture from the textbook, and this is the specific device for storing energies, I think. Oh, okay. let's go back to the another topic. Not another topic. It is a topic we have studied in the first semester. Energy stored in a spring. If there is a spring and spring is displaced by its equilibrium position by amount of x distance, the property of spring is that if it is compressed by a amount of x from its equilibrium position, then the force acting on this position is proportional to the displacement times k. K is the spring constant. The force generated by the spring is x times k. That's the property of a spring. So force as a function of displacement is just k times x, where x is the displacement of a spring out of its equilibrium position. Energy stored in this system is force times the distance, so energy stored in this spring by compressing it from its equilibrium position to a certain distance x is just force times the x integral, but force is kx, so k comes out of this integral, and x dx is the integral we need to have. That is just 1 over x squared. So energy stored in the system is 1 over 2 kx squared, where k is the spring constant. If we represent this in terms of force, then 1 over 2 force squared over k. That's the energy stored in this system. It is very similar to the energy stored in the capacitor, because U is 1 over 2 C times V squared over 1 over 2 Q squared over C. So this is very similar to the expression for the energy stored in a spring. So if we represent the energy stored in the capacitor in a similar way to describe the energy stored in a spring, we have similar expression. U is V times dq, and since V is 1 over cq, instead of kx for a spring is 1 over c times q. So k in the spring k as a spring constant of a spring is like 1 over c for a capacitor. So we have this relation. So voltage across a capacitor is 1 over c times q, where the force across a spring is k times x. So k is like 1 over q, 1 over c. So we have this relation. So the energy stored in a system is like energy stored in a capacitor. Here energy is stored in terms of Q, 1 over 2, 1 over c, q squared. Here energy stored in terms of x displacement. This is 1 over 2 k x squared. So the mathematics behind it is identical. Right, there are some topics. If we have if there is a capacitor charged with Q0 for a given capacitance C1, 8 microfarad, by applying voltage 112 volt, because because C is Q over V, Q is C times V0, so 8.0 microfarad times 112 volt gives the how much charge in coulomb stored in the system. If I connect this to another capacitor whose capacitance is 4.0 microfarad, we can calculate what is the voltage across the system after I switch this switch on. Total charge stored in the system is same before and after it's switching, and because this is a parallel connection of two capacitors, total capacitance is C1 plus C2, and total charge is before and after it's the same, so we can calculate voltage as the total charge divided by the total C, and we have this, so we can calculate the voltage after the switching. That's another example, exercise example. V0 is 112 volts, C1 is 8, C2 is 4, so it is 8 divided by 12, so that's 2 over 3 V0, so 2, that's 8 over 12 times 120, so it's 80 volt. Total voltage across this device after switching is 80 volt. That's what we obtain from here. And we consider the case where two plates are separated in vacuum, but most of the capacitors are filled this space between the two plates with a dielectric medium, where if there is a dielectric medium, dielectric medium is characterized by relative dielectric constant K with a C over C0. So new C is K times C0. If we have a 10 microfarad as a capacitance of this device, when there is a vacuum between these two plates, if we fill this space with a relative capacitance K which is 100, then capacitance for this device with the dielectric medium whose relative capacitance, relative dielectric constant K is 100, then capacitance is 100 times larger for this device. That's what we have. Normally we put a dielectric medium, and there are several dielectric medium whose relative dielectric constant is given like this. For a strontium titanate, we have 300 K values. So we have, for water, we can, by putting a water, we can increase the capacitance by 80 times, or this material we can increase the capacitance by 310 times. And the reason why we have a larger dielectric constant, relative dielectric constant, is because of the properties like this. For water, not water, CO2 or N2 or O2 gas, by applying, they are all neutral. At the center there is a positive atom, and we have a negative electrons around it. as an electron cloud. But if I apply electric field, the center of the electron cloud and the center of the nucleus of atoms are separated like this. It is proportional to displacement of these two charges are proportional to the electric field applied to it. If I apply a medium electric field, separation is small. For small electric field, separation is small. Medium electric field, separation is medium, and larger electric field, the separation becomes largest. There is another type of molecule which has its own polarity, like the water and hydrogen fluoride and ammonia. They have its own polarity. Center of electron cloud and center of the nucleus of atoms are not same, so they initially have separated value like this. And by applying electric field, the separation becomes a little bit larger, but its alignment is changed. So by applying larger amount of electric field, the polarized molecule aligns along the electric field. So we have a larger and larger alignment of this polarized molecule as we apply electric field. And anyway, regardless of the principle for these two different molecules, by applying electric field, we have alignment of negative and positive charges within molecule like this. And then by applying electric field at within the medium, plus and minus charges are cancelled, so there is no charge effect within this medium. But at the end, we have all minus charges aligned here, all positive charges aligned here. So the total amount of charge, net effective charge on this side is, without this molecule, if this is capital Q, with this molecule, Q is modified with Q prime, and so on. If this molecule is perfect metal, then K becomes infinite, and there is no electric field within it, because all minus charges here are cancelled out with positive charges. So we have a large electric field between this medium and the plate, minus charge plate, but there is no electric field inside. But in general dielectric medium, it is not perfectly cancelled out, but electric field within this medium is reduced much by the dielectric medium. That's how we have a modified electric field or charge by putting a dielectric medium. Electric field is reduced by amount of K, and we can calculate the amount of the induced charge density over here. So net electric field is, by using the Gauss law, sigma minus sigma induced over epsilon 0. This is sigma induced, which has the opposite sign of the charge density of minus sigma. So we have this, that is E0 over K. So that is sigma over epsilon 0 times K. So by using this equation, sigma I can be calculated as sigma, original sigma, times 1 minus 1 over K. That's the amount of the induced surface charge density by dielectric medium whose relative dielectric constant is K. So this is another example related with capacitor. Right. With or without the dielectric medium, Q prime is the charge with the dielectric medium. Q prime is same as Q. Electric field is reduced by electric field over K. K is about 100 in a good dielectric medium. C is Q over V, so C prime is K times C. So we can increase the size, the magnitude of capacitance K times larger than C. C is the capacitance without any dielectric medium, and K is about 100, so we can increase capacitance 100 times or sometimes 300 times. V is V over K because electric field is E over K. So the energy stored in the system is Q square over C prime. So Q prime is same as Q, so and C is just K times C, so total energy stored in the system is U over K. So it is reduced by the by 100 times. But charge is same, so the purpose of capacitor is to store charges with as small amount of energy possible. That's the purpose of a capacitor, and we need to make K as large as possible. Right, but any dielectric medium, we have a breakdown voltage or breakdown field. So breakdown field. There are breakdown field, maximum electric field we can apply before breaking its structure. It is like lightning. In air, lightning electric field to generate lightning is given, it's not given here, but for any given material, air, for example, before its breakdown or before it starts lightning, we have certain maximum amount of electric field for a given medium, and for the given relative dielectric constant K, there are the maximum breakdown electric field we can apply. So there is a maximum voltage we can apply, and there is the maximum storage we can use before its breakdown. That's the breakdown voltage. That's about it. So we covered the capacitance properties and the energy stored in a